Good afternoon, everyone. Good afternoon, everyone.
Good afternoon, sir.
Thing say,
Yeah, yeah. Let's continue where we left off last week. Um, we are going to do more conversion for moles and and atoms. Last week, um, we learned how to do some work, but we'll do some small revision before we delve into more detailed conversion for moles. When we are giving moles of atoms, and then we turn it into grams, and then grams of atoms we turn into moles. And we're also going to look at uh, when when you have the molecules of atoms, molecules of a substance, and then we turn it into moles. We use the Avogadro number, to do all those conversions. All right. So let's start with these examples. Now we're doing more examples to see how all those concepts that we learn before they are applied. Okay. So let's start to do conversion. The first example is converting between moles and number of atoms. All right. Uh, we are given a silver. Let me put it in a presentation mode. You have a number of atoms. We have a silver ring, right? A silver ring. It contains 1.1 times 10 to the power of 22 silver atoms. And you are asking how many moles of silver are in this ring. All right. So uh, whenever you are given a problem, you have to think about what you are given and what you are looking for. That's one of the strategies that you adopt. And then you find out if I'm given this and I'm looking for this, then how will I be able to, get what I want? What are the necessary equations? What are the necessary conversion factors that I need to adopt so that I can get what I'm looking for? All right. So in this case, so once we have the silver atoms, we have atoms. All right. And then this number we call the Avogadro's number. All right. Which is 6.02 times 10 to the power 23, right? Particles per mole. All right. So that Avogadro's number, right? We talked about this Avogadro's number when we were doing this gases. All right. That 6.02 times 10 to the power 3 is a very powerful number. We used to do a whole lot of work, a whole lot of conversions. Okay. So now we have this atom. We are giving 1.1 times 10 to the power of 22 silver atoms. And I want us to find the moles of silver. All right. Most of that silver. All right. So then we draw a solution map. All right. That solution map helps us a lot. All right. In the engineering or in the chemistry and all those sciences, right? It's good to in the other part, right? We call it algorithms. All right. But we say solution map. It doesn't matter what you call it. But the fact of the matter is when you draw stuff like that, it helps you to move you from one point to another. So this one point, or block diagram. When you come up with your studies, you see that, oh, okay, let me use this block diagram. From this point, I'll go to this point. From this point, I'll go to that point. From that point, I'll go to that point. Some of them are loops, whereby you have to go back to where you started from, especially when you are doing process dynamics and control. You need to use all those, those loops, feedback loop, and then feed forward loop, and a whole lot of stuff. You get it. I don't know whether you guys have started doing those um, the those strategies to do the work. All right. So we draw the installation map, silver atoms, mole atoms to the most atoms, right? So we have 1 mole of silver atom is equivalent to 6.022 times 10 to the power of 3 silver atoms. All right. So this is our solution map that we are going to use. All right. So when we have this, all what we need to do is just by the the number of atoms that was given here in silver. Then we get the moles. All right. So we have 1.1 times 10 to the power of 22 silver atoms. And then it's 1 mole of silver atoms, which is equivalent to 6.02 times 10 to the power of 3 silver atoms. So that gave us 1.8 times 10 to the power minus 2 moles of silver. All right. So is there any question on this? Then we'll move on to do another work. All right. If there's no question, let's move on and do something else. All right. Then we check the units. All right. Whenever you finish in engineering, the units are very, very important. All right. Why am I saying so? I'm saying so because you see, when you say a one, what does one mean? It means nothing. When you say, and you see one, when I say one city, there's this difference between one city and $1. So if you take my one city, it won't pay me. Right? One city is nothing. If you say 100 cities, 100, you can say 100, but if you don't put the units there, it means a whole lot of stuff, right? Or it means nothing. But when I say $100, $100 give you about 1,000 Ghana cedis. You get it? So units are very, very important. In the engineering work, we use units also to check, to see whether whatever we have done is correct or not. All right. So this one, we are looking for moles. We end up grabbing moles. So that's correct. Right? The units of mole of silver are the desired units. The magnitude of the answer is orders of magnitude smaller than the given quantity because it takes many atoms to make a mole. So you can expect the answer to be orders of magnitude smaller than the given quantity. All right. So you have to also check the physical sense that it makes. Some people, when they do a work, as soon as they get number, then they just leave it the way it is. All right. That one you wouldn't know whether you made it, as soon as you get a number, then you're okay. You can get a number though, but then what your number be bigger. So check to see whether it makes physical sense. All right. Check to see. If not, then you get a wrong answer. All right. So you can use this example to build your skills, right? To build your skills. All right. Let's do another one. All right. Calculate calculate the number of moles of sulfur in 57.8 grams of sulfur. Right. For that one, first one, we are giving moles, right? And we wanted to convert it into silver. We wanted to convert it into grams. Now we are giving grams. We want us to convert it into moles. All right. It's the same conversion strategy that we use, right? Look, you are giving 57.8 grams, and I want to find moles. All right. So you should also draw the algorithm, right? Or solution graph or block diagram or whatever to say, okay, I have grams. Then I'm looking for moles, right? Grams of what? Grams of sulfur. And I'm looking for moles of sulfur. Then you look the molar mass of sulfur. You go to the periodic table, you can get a molar mass of the sulfur, and you use it to do the work. All right. You need to do the work. So 1 mole of sulfur is 32.06 grams of sulfur. Then you take the grams and you multiply by it, then you are good to go. But you first have to know, right, the strategy you are using. All right. So you sit down for a few minutes, use the strategy. What strategy and what am I looking for? How is being given to me? Then you strategize that way, and then you can get your answer correctly. All right. So now we can solve it. All right. So we solve the solution map to solve the problem. You begin with 57.8 grams of sulfur and use the conversion factors to determine the moles of sulfur. All right. So we have 57.8 grams of sulfur times 1 mole of carbon. And then you have 32.06 grams of sulfur. All right. Then you cross multiply, you cross divide, and then you multiply. Then you get 1.80 moles of sulfur. When you finish, you check your answer. right? And make sure it also makes physical sense. If it doesn't make physical sense, then you go back and double check it. All right. So let's see if you can do this now. Everybody get to work and let's see. Calculate the number of grams of sulfur and 2.78 gram moles of sulfur. Everybody get to work and let's see how you get that answer correct. All right. Everybody get to work now. Calculate the number of grams of sulfur in 2.78 moles of sulfur. When you finish, let me know. And you provide us the answer. You show us how you did it. All right. So let's all do the work. Is Kingsley on Kingsley, are you there?
Sir, please, I'm here.
Good. Yesterday I didn't hear from this guy. Philip. Philip, are you there?
Oh, yes, sir, yesterday I was contributing. No.
So how come I didn't hear your voice? Because you always contribute, you know. So I was kind of, I don't know, maybe.
Yesterday I joined.
Oh, okay. When you finish, let me know so that we can see whether the answer we had was correct or wrong.
Sir, please, the most 2.7.
Yeah, 2.7 moles of sulfur.
Okay.
So I'm done.
Yeah. Engineer, what did you get?
So I get uh
Sir,
Yeah,
so I,
Kingsley.
I I got 8.8
sir, please,
9.1.
I got 86.58 grams.
And engineer, how much did you get?
89.1.
89.1.
Yes, sir.
Okay, engineer got 89.1 grams. And then was it Emmanuel who said that? Emmanuel, how did you get?
No, it's Kingsley.
Oh, Kingsley, how much did you get?
86.58 grams.
5.8 grams. Oh, okay.
8658.
Okay. And then who else? Everybody should do it too. Because in my exams will be coming, and I'm going to be setting questions. Matter of fact, I finished setting the questions anyway. So you have to be expecting those kind of work. You get it? So when I say everybody should do some work, at least participate. Do your own too. We'll discuss it, and then you also do your own too, so that it will
Sir.
help you yourself. All right. Even if you don't say it, we'll discuss about it. And then once we discuss about it, you compare with your answer. If you get it right, fine. If you don't get it right, how come I didn't get it right? Then you go back and check. Maybe you make some mistake. Maybe some calculation error. Maybe your calculator gave you error. You also have to learn how to use your calculator. Please. You understand? It's like you having a gun. If you're a soldier, you go to war and you don't know how to use your gun, the enemy will kill you. You get it? So you have to also know how to use your calculator and all those things, so that when you get exams is coming in the next 3 weeks or so, you'll be able to use the work to do. All right. So please, when we are doing, try to do some. Someone wants to talk.
Yeah.
So I got 85.5.
85.5.
Yeah.
85.
Hello, sir.
Yeah.
Yes, Alice.
I also had 86.562. So 86.56.
0.56. Okay. All right. Me too. I did it. Me too. I have 86.562 grams. All right.
Yes.
So approximately it's about 86.57 or 0.56. All right. Which is not bad. It's everybody is closer to the answer. But please check your distance. Check your calculations. Maybe the numbers on the periodic table. Let me tell you this. The molar mass on the periodic table, right? Sometimes the numbers they approximate it small, depending on the periodic table that you use. Do you get it? So when we are doing work, and we are all close at 86, 85, 86, 80, 87. You're okay. You're on a ballpark. I remember the last time I gave my students some exams. End of semester exam. One was he said the answer is so and so, but it was very close to the multiple choice, right? Very close to the answer in the multiple choice that I gave them. It was a multiple choice. So if that one is very close to it, so why don't you choose that one? Because it was very close. It was just maybe 1 point or so different, or maybe one number different. Then maybe there was some rounding off or something. So then you choose that one. So now basically it's very close. All right. So check. If you didn't get 86.582, 562, then see whether the molar mass that you use was a bit different from what we use or something. All right. So well done, everybody. Let's move on to do some work. All right. Let me see. I'm putting in a presentation mode so that you can see bigger. Converting. Now you are going to do converting grams and number of atoms. Yeah, converting grams and number of atoms. How many aluminum atoms are in aluminum can? Right. The mass of 16.2 grams. Somebody has given you aluminum can. All right. And they say the mass is 16.2 grams. How many atoms there are? Now, very simple, but very, interesting question. All right. So you are given the mass of aluminum and asked to find the number of aluminum atoms. We have 16.2 grams of aluminum. That's how it will give it to us. All right. And then we are trying to find the number of atoms in that aluminum can. All right. So now we strategize. Like I said before, I'll keep emphasis on it. You draw your solution map. All right. The solution map has 2 steps. right? In fact, the first step convert aluminum grams to moles. All right. You see, because if you don't do that, we have like I said, 1 mole of an element, right? I'm coming. I see that my children are doing some things that just mm, gentlemen, sorry for that though. I had to pause, because as a parent, I'm in a house and I've locked myself in one room, but I hear some noise going on, so I had to attend to it. You know how these kids they behave. So sorry if I had to pause because I don't want to go to the hospital this afternoon. All right, so pardon me for that. So how many aluminum atoms in that? So you have to strategize, right? You have this powerful conversion factor, all right? Very powerful. 1 mole of an element, right, has this atoms, number of particles, which is 6.02 times 10 to the power 23, the Avogadro's number, all right? So think along that side. Don't sit there and be like, oh, what do I do? All right. So think along those sides. All right. So you are given a mass of aluminum asked to find the number of atoms. So you have 16.2 grams of aluminum, and then you are trying to find the aluminum atoms. So what's the relation do I have with the grams, the grams and then the atoms? All right. But I have to go to somewhere else before I can get to that place. For example, I'm coming to, I'm in a GC2 main campus. I'm coming from a West Hills Mall. I know I cannot just jump. I'm taking cars, but if I don't take any, dropping straight, and I have to, there's no any dropping car, so I have to make a transit. I'll make a transit at maybe La Paz, or I can make a transit at Circle. Then I take another car. Then I come to main campus, or I take another car from La Paz and come to main campus. Same thing. You cannot have any relationship between the grams and then what, and then the atoms right away, just like that. But then there's another relationship between the moles, all right, the moles, and then the grams, and another moles, and then the atoms. So then I'll go from one step to another, and then from one step to another. That's how we solve problems. That's how we solve engineering problems. All right. So you go to this place and you see that relation with the other one, and then you pick that one, and you see that other relation with the other one, and you pick that other one. So then you get into the end. Do you get it? So now we have 1 mole of aluminum atom. So you use the molar mass, right? 1 mole of aluminum, right, is equal to 26.98 grams of aluminum. All right. So now I'll convert it into moles. Now, once I get the moles, now I need atoms. So 6.02 times 10 to the power 3 aluminum atoms is 1 mole. Then I know I'm in good business. All right. So that is the solution map. All right. So once you get that solution map like that, the rest of them is just calculations. Then use your calculator, within some short time, then you finish your work. All right. So now you have this. You have the relationship that I told you already. All right. So now solution is 16.2 grams of aluminum times 1 mole of aluminum, right? Divided by 26.98 grams of aluminum times, right? 6.022 times 10 to the power of 3 aluminum atoms divided by 1 mole of aluminum, right? Which is equal to 3.62 times 10 to the power of 3 aluminum atoms. Any question? We check the units though to make sure the units are correct, and we check the physical sense. Okay, we check the physicals and make sure it makes sense because they're asking us for aluminum atoms. In the end, lo and behold, we have aluminum atoms. All right, and now let's see the listen. There's another work that we have to do. We have to calculate the mass of 1.23 times 10 to the power 3 aluminum atoms. All right, so let's everybody get to work. Helium. Let's get to work and see how we can get it. All right, everybody get to work. Calculate mass of 1.23 times 10 to the point 24 helium atoms. The mass of it. Now they've given us atoms here. So now let's see how much of the mass of it are we going to get. All right. Everybody get to work. Molar mass of helium.
So I've gotten 8.18 gram of helium.
8.18
18.
grams of helium, right?
Yes.
Okay. Let's wait for our friends also to work small to see how they also come up with what they will come up.
So I got 8.16 grams.
Okay. Someone also got 8.16 grams. All right. Anybody else? Anybody else?
Hello, sir.
Yeah.
I've also gotten 8.16
So that means
grams.
everybody is correct. All right. Everybody is correct. So how did you get the answer? Who can tell us? Who can tell us? Who can tell us how he had his answer? Engineer, you are the one who came first. Engineer, tell us. Philip.
Yeah, sir. Sorry, I went to the washroom.
Hey, Philip. So soon.
Okay. Okay, sir. So with this one, we have to use the Avogadro's. You have to use the Avogadro number.
Use Avogadro's number. Okay.
Yeah.
Okay, good. Use Avogadro's number. Who can continue where Philip ended? And then use Avogadro's number to get what?
So we use the Avogadro number to get the mole of the mole.
Okay, and then once you get the mole, then what else? Then what else? Who's
Sir.
gonna help Philip? Uh-huh.
So after using the Avogadro constant to get the mole, then we also
Well,
need the molar mass of helium,
very good.
which is
And
4.0. Then
very
we use to
good.
multiply the moles, then we get the final answer.
Well done. Well done, guys. Everybody, well done. See, now you understand, you understood the concept. It's very, very, beautiful to get those concepts done. Because when you do chemistry and you get those concepts done, it carries you up. All right. It carries you up. Now let's see. Uh, let's just say. We are going to do more. Let's see, but this thing is blocking my view. Let me see. Let me go back and see something. Now let's do this. We'll calculate mass in grams of 1.7 moles of water. Right? Calculate the mass in grams of 1.72 moles of water. All right. So we have the moles of water. And then we are going to calculate the number of grams of it in water. All right. So that's what you are given. You are finding the grams of water, you have the moles of water. This one is very simple. All right. You have the moles, and the moles is going to give us grams. That's the solution map. All right. So now we need the molar mass of water. You go to the periodic table and you see H2O. You see the H2O. All right, so 18.02 grams of water is 1 mole of water. How do we get 18.02 grams of water? You just say, okay, 2 atoms of hydrogen and 1 atom of oxygen, right? So 2 atoms, the atomic mass of hydrogen is 1.01, all right? And then atomic mass of oxygen is 16.00, right? So then this one is two of them, the H2O, 2 hydrogen. Multiply the 2 by the 1.01, and then you add it up to 1 times 16.00. And when you add them up, you have 18.02 grams per mole. That's the molar mass of water. All right. And that molar mass of water is 1 mole of water. All right. See how the moles are. The moles is very thin. A very funny thing that we deal with. So if you don't see the mole concept like this, you cannot enjoy chemistry. You understand? But chemistry can be very enjoyable if you understand the concept in it. Things become so easy for you. You got it. So 18.02 grams of water is 1 mole, and that 1 mole two becomes 6.02 times 10 to the power of 23, and that 1 mole two becomes something like maybe 12 grams is 1 mole. You see that mole thing? It's very, very fun. So you just understand how the mole works, and then you'll be happy working with it. You got it. So now 18.02 grams of water is per 1 mole of water. All right. So then we use this to strategize and then do our work. All right. So we have 1.75 moles of water times 18.02 grams of water per 1 mole of water. We do the cancellation and multiply, we get a 31.5 grams of water. Any question on this? Right? Like I said, when you do it, the work, you have to also check whether it makes sense, right? If it makes sense, all right, then you move on. If it doesn't make sense, then we do. Okay, now let's also try this. Calculate the number of moles of nitrogen dioxide in 1.1 gram mole, 1 grams of nitrogen dioxide. Let's get to work and try. Everybody, let's work. All right, everybody, get to work. Everybody, get to work. When you finish, you let us know. Whoever will finish first. You let us know, then we all calculate it. Who has finished?
Sir.
Yes, don't go.
Yeah. So should I mention the answer?
Yeah, go ahead. Go ahead, because we
Okay,
will
so I
compare
had 2.5, say 2.56 times 10 raised to the power negative 2 moles.
2.56 times 10 to the power of minus 2 moles. Okay.
Yeah.
Anybody else?
Yeah, same answer, sir.
Oh, okay. Who else? Did somebody had a different answer? Did somebody get a different answer? I think me too. I had the same answer like yours. So, yeah, who is talking? I see somebody wants to talk. Somebody's talking. I mean, to have the same as I have 2.56 times 10 per minus, so 0.02566 moles of nitrogen dioxide. All right. You guys are doing a very fantastic job. Well done. Well done. Is Yara there? The only female among us. Yara, are you there? Yara, who has here from her? Engineer. No, let me ask Kingsley. Kingsley, you are the class rep. Where's Yara? Kingsley. Kingsley. Oh, Kingsley is gone. Let me see. Let me check the list here right now. Participants. But Kingsley is there. He's not responding. Sadat.
Hey,
Sadat, have you heard from Yara?
no, sir.
Oh, how
But
come?
initially, she was with us. She was with us during the, I think, the computer period. And the
So
period.
she ran away from my class.
Oh, I don't know what could prevent her, though.
Because the last time, all this time, I've been asking for her, but she doesn't show up. There's a number of times that when a student is out of their class, the person is not permitted to write the end of semester exam.
Oh, okay.
Yes, it's true. You'll find out if the student is out for about 3 times or so. The student is not allowed to write the exams. All right. So if you have any challenges of not coming to lecture, you have to let me know. See, you guys are not many, so I know all of you. All right. And then attendance is here.
I will communicate with PC and
Yes.
see the way out.
Exactly. The attendance is also here. So if you are unable to come, you have to let me know. And then we see the way forward. Because if you stay away from lectures for 3 times, you'll not be permitted to write the end of semester exams. Because if you bump so badly, we're trying to do assessment to see why a student is not really performing well, whether the student doesn't understand the work, do you get it? Or the student is not really working. Do you get it? Or the lecturer is not really do the work well for you guys. So then, if you keep staying away from lectures, all right, then that you will not be permitted to write it, and because it's like work, right? You guys are workers. You guys are workers. So because you guys are workers, we assume that you are doing correctly. But under normal circumstance, if you have a job and then you don't really attend the job for maybe 2 times, your boss doesn't hear from you. 3 times, your boss doesn't hear from you. Do you think that your boss will leave the job for you? That anytime you sit home, anytime that you're ready, you come to work? No. I mean, if you are the employer, I don't think you'll be happy for that. Now, for somebody to stay. Yeah. So, you want your job to proceed. Same thing with the school. Yeah, Sarat, it's true. You have somebody to work on your fish farm for you. The person doesn't come the first day. The person doesn't come the second day. The person doesn't come the third day. Then you are sitting waiting for the person. You find somebody else to come and work for you. You see, so please let her know. It's not like I'm singing her out, but then because she's only the female in our class, that's why we come because we hardly get engineers. Yes, nowadays girls are getting interested in engineering, but most of the time we have about 100 students. Only about 5 of them are male. 5 of them are female, and the rest are male. You understand? So we try to blend it. So let her know. All right. Anyway, let's keep on. I think everybody, the answer you had was correct. Unless you are doing good job.
Basek, please, with the answer being Let me check because I think with my own, I did it to three significant figures to
Figures.
0.0257.
Yeah, that's okay. That's okay.
Okay.
It's okay. Let's do more work. The mole concept, converting mass of a compound and number of molecules. What is the mass of 4.78 times 10 to the power 24 nitrogen dioxide molecules? All right. Now we are from atoms. Now we've come to molecules, and you see, you know. So now you are given the number of nitrogen dioxide molecules and asked to find the mass of it. All right. So we have 4.78 times 10 to the power 24 nitrogen molecules. Our strategy, right? The solution has two steps. It has two steps. All right. We have the moles of nitrogen dioxide and one mole of nitrogen dioxide. That's why I say that mole thing is a very funny guy. The mole, that Avogadro's number. The same moles is becoming molecules. So that's why we say 1 mole of a substance, per 6.02 times 10 to the power 3 particles of that substance, right? So now the moles has become molecules. 1 mole of nitrogen dioxide is equivalent to 6.022 times 10 to the power 23 molecules, all right? And once you get the moles, then we convert the moles we use the molar mass of it, right, to get the grams of it. You see how beautiful it is. So if you understand that mole concept, it helps you a lot, all right? So now we have our solution by 1 mole nitrogen dioxide divided by 6.02 times 10 to the power 23 molecules, and then we have 46.01 grams of moles of nitrogen dioxide. Then we have 1 mole of nitrogen dioxide. All right. So now let's put the words together. Let's put the numbers together, and then we move on. 6.02 times 10 to the power 23 molecules is equal to 1 mole of Avogadro's number. All right. So the number of nitrogen dioxide molar mass, right? Nitrogen, that atomic mass is 14.01. Oxygen is 16. 2 of oxygen, 2 atoms of oxygen, 1 atom of nitrogen. Multiply them together, multiply them and add them together, then we have 46.01 grams per mole. Now that's what we are going to use to get our final answer. So now we are given 4.78 times 10 to the power of 24 molecules. 1 mole of nitrogen dioxide is equal to 6.02 times 10 to the power of 23 molecules of nitrogen dioxide. Yeah. Yeah, Philip. Philip, are you talking?
Yeah, it's Philip.
Yeah, Philip. Go ahead.
Sir,
Talk.
please. Sorry, I want to know the answer for the last one we did before.
The answer was 0.02556 moles.
Okay.
Yeah. Some people use this scientific notation, which is also acceptable. So in any way, you have to know how to convert from that smart way to use a scientific notation. All right. If it's scientific notation, you have to know that one. I thought, you guys know that one, so we didn't waste our time, to really do the scientific notation kind of stuff. All right. So I just, but then some people give the answer, in scientific notation. All right. So now we have 4.78 times 10 to the power 24 molecules of nitrogen dioxide times 1 mole of nitrogen dioxide per 6.022 times 10 to the power 23 molecules of nitrogen dioxide. All right. From there on, then we use the molar mass, which we calculated from here. All right, from the top here. All right. Then we say multiply by 46.01 grams of nitrogen dioxide times 1 mole per 1 mole of nitrogen dioxide. We do the multiplication, cancellation, and stuff. That one is just very trivial. All right. Then we get 365 grams per of nitrogen dioxide. Like I said, when you finish, don't just jump to conclusion. If it's multiple choice, you may not see your answer there. Then you say, hey, what did I do? Let me go back and check. But then if it's not multiple choice, right, and it's just written, and then you write it and you just leave it like that, you may be wrong. It's not because you didn't know how to do the work, but because maybe there was some calculation error somewhere. So you go back and check to make sure this one makes physical sense, right? Check the units, make sure the units are correct, and check whether it physically makes sense, all right, before you go ahead and then you present your work. Because when you do the final work, you give me the work, but you wouldn't know whether I did it right or I did it wrong until your grade comes. So, oh, I thought I knew it, but how come I get some work? Sometimes I'll be marking some students' work. I knew the student was good. You understand? But then, they make some silly mistakes. So, why does this student make this mistake? Why does this student make that mistake? So please check your work before you submit your work. Okay. Imagine the same way you are working in a chemical lab. All these things that we are doing is what you are going to do when you have some work in maybe chemical lab or something. Yeah, the same thing. It's nothing different. You get it, and then you just do your work. You get some bogus number, and you're still using that. You're still using it. You don't check to see whether what you're doing is wrong, and then you present your work to whether your boss or whatever. And if you are a boss too, you have to go over them. The work that you guys are doing, I'm also doing it where I'm sitting, to make sure we all come to the same thing. So if I don't know how to do it, how will I be able to help you guys? So you also have to know how to do it so that, just in case you are by yourself and you are doing some work, you can really check and say, oh, okay, I'm right. Or, you know what? Oh, I'm wrong. What am I wrong? Getting something wrong, in the first place doesn't mean that that's the end of the world. Please. When you get something wrong, maybe your frame of mind that time did not permit you. Even as I'm talking, sometimes your mind may deviate from or may move from what I'm saying, and then you may be thinking about maybe your work, or maybe your children, or maybe your wife, or maybe when you are coming to your home, somebody push you around. Maybe some driver on the road, honk his bell, a bell on you, and then you kind of your mind can go there and then come back quickly, or maybe sometimes you stay there for some time and you come back. You get it. So getting it wrong at the first time instant doesn't mean that that's the end of the world. You can just go back and check and see where you made the mistake, and then you correct yourself, and then you move on. All right. So let's see whether let's do another one. All right. Chemical formula as a conversion factor, converting between most of a compound and most of a constituent. All right. The students find it so tough to understand it, but it's very simple. If you follow what we are doing now, right? Determine the number of moles of oxygen. We are going to determine the number of moles of oxygen in 1.7 moles of calcium carbonate. All right, you have calcium carbonate, and then we are going to determine the number of moles of oxygen in that, the 1.7 moles of calcium carbonate. All right. You know the moles of calcium carbonate, and then you are going to use it to find the moles of oxygen. All right. So you strategize. Like the strategy, always try to use the solution or the solution map or the that algorithm or the block diagram. All right. And those things. This one, like I said, you can call it anything you want. See, once you look at it in the formula, right? The chemical formula that you have there, you have Ca, calcium, and C, carbon and oxygen, right? Calcium, carbon, oxygen. you see that you have a number of atoms of oxygen. There are 3 atoms of oxygen inside that compound, right? Inside that compound, see 3. 3 of them are here inside that compound last year. So you say 3 moles of oxygen is per 1 mole of calcium carbonate, right? 3 moles of oxygen per 1 mole of calcium carbonate, right? So from moles of calcium carbonate gives you the moles of oxygen. All right. So this is the conversion factor that we are going to use. All right. See how moles is funny, how to use it. So that's why we are studying it. We are just strategizing this here. So 3 moles of oxygen is 1 mole of calcium carbonate from the chemical formula. All right. So now we have 1.7 moles of calcium carbonate. All right. Then we multiply by 3 moles of oxygen per 1 mole of calcium carbonate. That gives us 5.1 mole of oxygen. So that's how we're using this to do our work. All right. Then you check to see whether it makes physical sense. And then we'll keep on moving on. All right. Determine the number of moles of oxygen in the 1.4 moles of hydrogen sulfate. Can we do this? All right, everybody, let's get to work. Let's all do it. We have 1.4 moles. 1.4 moles of what? Of H2SO4, sulfuric acid. And then we are going to find the number of moles of oxygen in them. All right. So everybody get to work and let's see. All right. When you finish, let us know. When you finish, let us know.
So I got 5.6.
Okay. Alex has 5.6. Does anybody else get something else from what Alex had? Anybody else? Anybody get something?
So 5.6 moles.
Okay, engineer 2 got 5.6 mole of oxygen. Who else? Kingsley, what did you get?
5.6.
Okay, good. I think me too has 5.6. Right? Actually has 5.6 moles of oxygen. All right. Very simple. All right. See this mole, like I said, very funny animal. Let's do another chemical formula conversion factors. All right. All right. As a conversion factor. Carbon. This chemical formula is C10H4, H14, and then O. Carbon is the main component of spearmint oil. Right? It has a pleasant aroma and mint flavor. Carbon is added to chewing gum. All right, that's why we have the chewing gum that we chew, and then we put in liquors and soaps and perfumes and a whole lot of stuff. Understand? And we are going to calculate the mass of carbon in 55.4 grams of carbon, right? We have the mass of carbon, right, which is 55.4 grams. And now we are calculating the mass of carbon in it. We are going to find the number of the mass of carbon in that 55.4 grams of carbon. All right. So we strategize. There's carbon. How many are 10 of them? Carbon. If you look at the subscript here, you have 10 of them. All right. And you have hydrogen 14, have oxygen 1. Those are the atoms. But remember, see, we are using that kind of mole thing. All right. So let's see what we are giving. We are giving 55.4 grams of carbon, right? Carbon. And then they want us to find grams of carbon in that amount of carbon that was given to us. So what we will do is this: we strategize it. We think about what are the relations. We have the grams. We convert the grams into moles. Then the moles of carbon, and then the moles of the carbon relationship. So once we get the moles of carbon, then we use the molar mass of carbon, all right, to get the grams of carbon. Let me go over it again. We have the grams of carbon. We have the grams of carbon. So the grams of carbon, right? It has carbon in it, all right? So let's see how we are strategizing. So we are using the grams of carbon, right? We use the grams of carbon. We change it into moles of carbon, right? So once we change the moles of carbon, right, then we see the mole to mole relationship of the carbon and carbon. Once you get the moles of carbon, then we use the molar mass of carbon to get the grams of carbon. All right. Then we are good. All right. So grams to moles, and then from moles to moles, and then moles to grams. All right. So that's how we do it. All right. So now let's see. Grams of carbon to moles of carbon, and then moles of carbon to moles of carbon, and then moles of carbon to grams of carbon. See, so it's 1 mole of 6C10H14. Oh, it's 150.2 grams of C10 carbon. All right. This is how you calculate it. We've done it before, and then we're just going over it so that everybody will be confident, whatever. Now, some of you have done chemistry before. Some of you too are new to chemistry. You understand? That's the most reason why most of the time I take my time and go over stuff, little by little, so that everybody can, those who have not even done chemistry before can know what is going on. All right. So the molar mass of carbon, right? We have 10 times, the carbon, which is 12.01. All right. And now we have 120.1. Then we say, okay, hydrogen is just 1.01 atomic mass. Then we multiply by how many of them? There are 14. If you look here, the carbon is 14 here. All right. So multiply that, then we get 14.14. Now we say, okay, oxygen is just the only one of it. All right. Oxygen is just one. And its atomic mass is 16.00. All right. And then we add them. So when we add them all, we have 150.2 grams per mole of carbon. All right. And now when we look inside the formula, we see that we have 10 moles of carbon, right? Inside the formula, right? 10 moles of carbon. So then 1 mole of carbon is 12.0 grams of carbon. Then we are good to go. Once we get all those conversion factors, the rest of them is just multiplication and start from the beginning. And then we are good. All right. So now 55.4 grams of carbon times 1 mole of carbon per 150 0.2 grams of carbon times 10 moles of carbon per 1 mole of carbon times 12.01 grams, of carbon, and it's per 1 mole of carbon. In the end, we have 44.3 grams of carbon, right? So that's how we get it. Any question on this one, then we'll move on to see whether, we can do some work on it, or we'll move on. Okay. Let me see the time that we have. Yeah. I was planning for us to do maybe an hour and a half. Let's see.
So,
Yeah, Nana. Let's see.
please, I have one question. So, when you got the mole of the carbon, how did you like deduce the mole of carbon through the carbon? So,
Nana, say your question again.
after getting the mole of carbon,
Mm-hmm.
how did you use that to get the carbon's mole?
More. Okay.
Is it
See, look at the formula. Let me go back to more. Now look at the formula. We have C10, H14, and O, right? Then do you see it?
yes, sir.
So the carbon, right? If you see that carbon, right,
Yes,
it's
sir.
1 mole of carbon, right? It's 1 mole of carbon, but it has how many atoms of carbon? C10. See that it has C10.
Yes, sir.
So is that 10? Is what we are using as the mole of the carbon.
Oh, okay, sir.
Do you get it? So here you see,
Yes, sir.
look at the solution right here. 10 moles of carbon is equivalent to 1 mole of C10, H14O. That's how you use to get the moles of the carbon. Do you get it?
Okay, sir. Yes, sir.
Good. Good.
Thank you.
You're welcome. So now that's how we do. So we multiply by this and then we get the answer. We try to see whether it makes physical sense. All right. So we check your answer. Are the units correct? Does the answer make physical sense? All right. The units grams carbon are correct. The magnitude of the answer is reasonable because the mass of carbon in the compound must be less than the mass of the compound itself. All right. Then we go and check to see whether it makes physical sense. All right. Let's do another example. Using my percent. Yes. Using my percent composition as a conversion factor. All right. The FDA recommends, FDA, Food and Drugs Administration, they recommend that adults consume less than 2.4 grams of sodium per day. That's what they are saying. They say we should consume less than 2.4 grams of sodium per day. Well, so how many grams of sodium chloride can you consume and still be within the FDA guidelines? All right. Sodium chloride is 39% sodium by mass. Sodium chloride is 39% sodium by mass. So if you take any sodium, all right, any quantity of sodium, 39% of, sodium chloride, sodium chloride. That one, if those people who don't haven't done chemistry before, they know sodium chloride is salt. All right. And they know H2O is water. All right. That one, a whole lot of people knows. So the FDA is telling that we should consume 2.4 grams of sodium per day. Are we maintaining that? Me, I don't know, because when I'm eating my salt, I don't even measure anyway. Sometimes when I cook or my wife cooks, we just eat it. We don't concern. If it's too much salt, we know it's too much salt. Your tongue will tell you. We don't do that calculation. Those who did catering and they do those kind of calculations, but we all right. So now you are giving the mass of sodium and the mass percent of sodium chloride. When the mass percent is given right as a fraction, right? So we are going to write it as a fraction, right? 39 grams of sodium is 100 grams of sodium chloride, right? That's how we do we'll write the percentage. If I say, oh, you had 5%, in your exams, let me say 5 divided by 100 is what you had. If I want to make it in the decimals, I will divide 5 divided by 100. That will give me 0.05. That's what you had as your marks, right? So percentage is any number, multiplied by 100 is the percentage. If I have 8, and what is the percentage of 8? That means multiply 8 by 100. You give you 100%, right? So if I have 39 grams of sodium, right? And then the total amount is 100 grams of sodium, and then I can convert it from that, the percentage into grams, all right? In chemistry and in mathematics, we do that way, all right? Instead of saying, okay, 39 grams of sodium or 39% of sodium and then 100 grams of sodium, you pick it in that way, right? So that means you can say it's 39 grams of sodium and then per 100 grams of sodium chloride. It's permitted to do it that way, all right? It's permitted to do it that way, all right? So now, once you have 39 grams of sodium per 100 grams of sodium chloride, and now we have how much? 2.49 grams of sodium per day. And how many grams of sodium? So we have to just simple. This is a conversion factor. You multiply by it and you can get our answer. All right. So we strategize drawing the solution map. All right. We have 100 grams of sodium chloride per 39 grams of sodium. 100 grams of sodium chloride per 39 grams of sodium. All right. So now we need how many grams of sodium chloride do we have to eat so that we don't go beyond whatever the FDA is saying we shouldn't go beyond. You get it? So now we multiply by the 2.4 grams of sodium, and that will give us the answer. All right, 2.4 grams of sodium per times 100 grams of sodium chloride divided by 39 grams per sodium, which is equal to 6.2 grams of sodium chloride. Any questions here? Any question here? Let's move on. You are given the molecular mass percent composition. Calculate the mass percent of chlorine in Freon 114, right? Freon has this form. This Freon, we put it in the refrigerators, the fridge, the gas in it, Freon. Or this in the ACs, those are the coolants, right? Freon. Right? Calculate the mass of chlorine in Freon 114. C2Cl4F2. You are given the molecular formula of Freon, which is 114, and asked to find the mass percent of chlorine. All right, chlorine. We use the same strategy, right? We have C2, C14, and then F2, and we have find the mass percent of chlorine. All right, so we strategize it. All right, we have the mass percent of chlorine equals to 4 times molar mass of chlorine. All right, per molar mass of Freon times 100. All right. This is there's a mistake. It's Cl4. It's Cl4. It's not C14. It's Cl4. All right. So if you look here, mass percent of chlorine is equal to 4 times molar mass of chlorine. All right. Divided by molar mass of Freon times 100. All right, molar mass of Freon. So we can use the same thing. Carbon, what is the atomic mass of carbon? And what is the atomic mass of chlorine? What is the atomic mass of fluorine? Multiply this by 2, multiply this chlorine by 4, multiply carbon by 2, add them all together, and then we know molar mass of chlorine, and then multiply by 100. Then we are good business. 100%. All right. So this is the relationship we use, the chemical formula into mass percent of chlorine. All right. All right. So 4 times molar mass of chlorine. Chlorine is molar mass, or this molar mass is 35.4 grams. If you multiply by 4, you have 141.8 grams. Molar mass of freon, right? Carbon 12, 12.01, multiply by 2. And multiply chlorine, right? That one, we have it already. Multiply by 35.45. That will give us 141.8. We have it already. And then fluorine is 19 grams per mole. So now we also multiply by 2 because it's two of them in the formula. All right. So adding them all up gives us 203.8 grams per mole. Now, the mass of chlorine is equal to 4 times molar mass of chlorine divided by molar mass of freon times 100. And doing all the calculations and little by little, we have 69.58%. All right. Then we look at ourselves. Does it make sense? Yes, it makes sense. Because chlorine, look at the molar mass of it, and then look at the other masses, and then see how many of them. We have 4 of them, and see that it will make sense because it's 69.58% of it that we have inside the freon. All right. So now you can do this, an empirical formula from experimental data. We have empirical formula, right? We have experimental data, and then we are going to use it to find the empirical formula. All right. Yes. You decompose a compound, right? You decompose it, a compound containing nitrogen and oxygen in the lab, and you produce 24.5 grams of nitrogen and 70.0 grams of oxygen. We are going to calculate the empirical formula of the compound. All right. I'm going to calculate the empirical formula of the compound. So you write down or calculate the masses of each element present in sample of the compound. If you are given the mass percent composition, assume 100 grams sample and calculate the masses of each element from the given percentages. All right. But in this case, we are given the grams of it. So we are good to go. All right, Sam. Now we don't have to assume 100 grams of the mass of that compound, but then because we already have the grams of the compound. So now they want us to find the empirical formula, and you are given the masses of them. You convert each of the masses step 1 to moles. This mole thing is very important. Everywhere moles. Okay. Convert each of the masses step 1 to moles by using the appropriate molar masses for each element as a conversion factor. Right? So we convert 24.5 grams of nitrogen into moles. Look for the molar mass of nitrogen, or atomic mass of nitrogen. This is 14.01, or atomic mass unit of it. All right. And now we have 1.75 moles of nitrogen. Oxygen, same thing, 70.0 grams of oxygen. That's 1 mole of oxygen. We have 16.0 grams of oxygen. And so we have the moles of it. All right. So now we are going to use them, to find the empirical formula of it. All right. So now the strategy 3 is to write down a pseudo formula for the compound using the moles of each element. Right. So now we have put that mole that we have under the subscript. Put it as the subscript. All right. So we have the nitrogen, we have 1.75, and oxygen, we have 4.38. All right. So now, once we have it this way, what do we do? Because we see mostly we don't put that, decimals there like that. So what do? What we are going to do is that we divide each of the substrates by the smallest number. 1.75 and 4.38. The 1.75 is smaller and 4.38 is bigger. So we are going to divide all of them by 1.75. Otherwise, if you divide by 4.38, you won't get your answer correct. You understand? So we divide all the substrates in the formula by the smallest substrate, 1.75. But that gave us the nitrogen is 1 and oxygen is 0.5. The substrates, they are not all whole numbers because 2.5 is not a whole number. So you're going to multiply by small, a whole number, right? A small whole number. All right. So then we say that, okay, 2.5, once you multiply 2.5 by 5, we can get 1 here. We can get 2 and then 5. All right. So this is a correct formula, which is empirical formula, which is N2O5, dinitrogen pentoxide. All right. So multiply the whole numbers by this. If you have, for example, if you have 0.1 multiply by 10, if you have 0.2 multiply by 5, 0.25 multiply by 4, 0.33 multiply by 3, 0.5 multiply by 2, 0.6 is. This is the strategy, right? The fractional substitute, right? If you have 0.1 multiply by 10, multiply the whole numbers by 10. If you have 0.2, for example, you have 2.1. I'll multiply by 10. I'll multiply all the whole numbers, the substitutes by 10. If you have, if I have 0.2, I'll multiply them by 5. Then I'll get the whole number. If I have 0.25, I'll multiply by 4. Right? Then remember this one, we have 2.5. So we have to multiply by what? By 2. If it's 0.5, I'll multiply by 2. 0.66, I'll multiply by 3. 0.75, multiply by 4. And that will help me to get the whole numbers. Right? It's a strategy we adopt. Okay. So now let's do this one, and then I think we can call it a day. All right. Obtaining a laboratory analysis of aspirin determines the following mass percent. All right. The mass percent of it, we have 60.0%. All right. We have 4.48%, and we have 35.53%. They are all in carbon, hydrogen, and oxygen. Right. So aspirin, right? Aspirin contains 60.00%, 4.48% of hydrogen, and 35.53% of oxygen. And we are going to use this to find the empirical formula of aspirin, CHO. All right. So write down or calculate the masses of each element present in the sample of the compound. So now, because we are giving percentages, we are going to assume 100 grams. Because we are giving the percentage, we are going to assume 100 grams. And then once we get the grams, we multiply 100 grams times 0.6. Multiply the 100 grams times 0.4, 0.048, and then we all put it in the, then we put in the grams of those listen. Because they are all sharing the grams anyway. Right? They are all sharing the grams. So why don't you multiply them and get in the grams? Once you get it, you multiply and get it, then you go back to the first formula that we used to get the empirical formula. All right, so let's keep on moving. All right. So 60 grams, they will take into moles. 60 grams of carbon times 1 mole of carbon is 12.01 grams of carbon. That gives us 4.996 moles of carbon. All right. Hydrogen, we have 4.48 grams of hydrogen, and it's 1 mole of hydrogen per 1.01 grams of hydrogen. It gives us 4.44 0.45 moles of hydrogen. 35.53 grams of oxygen. Multiplied by the moles, all right? 1 mole of oxygen is 16.0 grams of oxygen. That will give us 2.22 1 moles of oxygen. Then write out the pseudo formula for the compound. We put all the distance of the moles that we had at the subscript, right? At the subscript. And now we say that, oh, okay, the smallest one, right? We are going to divide by the smallest one. We have 4.44 moles, we have 4.996 moles, we have 2.221 moles, all right? When we divide by all of them, we had, we have C 2.25, H 2, and O 1, all right? We have this, decimals in there. And remember our strategy, we have to multiply. When we have 0.25, we look through this, 0.25. Which number do I have to multiply by 2.25 to get a whole number? Which number do I multiply by 0.25 to get a whole number? Then I will multiply by 4. Or better still, what I will do is I will divide 1 divided by 0.25. If I divide 1 by 0.25, I'll get 4. So now, if I get 4, then that's the 4 that I'm going to use. If I divide 1 divided by 0.1, I'll get 10. 1 divided by 0.33, I'll get 3. 1 divided by 0.5, I'll get 2. 1 divided by, that would be the easiest way for you to, not worry yourself memorizing all the 0.1 and 0.2 and the 0.5 and give it the next stuff. No, all you do is just, if you look at the, the decimal part, all right, the decimal part and divide it into 1, and that gives you which number you have to multiply by all of the subscript to give you the whole number, all right? I'm done for the day, okay? I'm done for the day, and God willing, we'll meet. So this is the score. Go home and do this. Ibuprofen. Who knows ibuprofen? Who knows ibuprofen? What's ibuprofen?
It is an inflammatory painkiller.
Yes, good, Sadak. Well done. Guys, go home and practice this one. The skill builder. Now I'm done for the day, and you're gonna have a good weekend. I'm also gonna have my nice weekend. I'm not, tomorrow I'll go to church though. I know those who are Christians will go to church, and then on next week, God willing, on Friday evening, we'll meet and then study our environmental study. You can, WhatsApp me if there's any problem. I'll WhatsApp you too if there's any problem. All right. Any question before we? Yes.
Sir, so we are you going to provide us with the periodic table so that we'll use it as a reference, or we have to memorize all those?
Engineer, you have to memorize the periodic table. No, I'm just playing. I'll give you the periodic table. Yeah, how can you memorize this periodic table? I'll give you the periodic table. That'll be so much, man. I mean, myself, I haven't memorized the periodic table. I mean, I know most of it, but I don't know all of them. So in case I'm doing exams, I'll give you the periodic table.
Okay, sir. Thank you.
And sir, please, if you may ask, do you have any past questions that we can also be trying our hands?
Oh, sir, no, me, I don't have any past questions.
We see, most of us, it looks like we are now getting familiar with the chemistry. You understand? So sometimes we try to enhance our knowledge on it small, so that at least as time goes on, we'll master it.
Oh, you already mastered it, See, the way you guys answer questions, I'm so happy, to be honest. You are really studying hard, and it's good, all right? So you do well, you do fine, okay? If you go by all the strategies that I showed you today, or all the rest of previous lectures, you do well. Okay, so don't worry. Yeah. All right. So I'll stop sharing this, and then we'll meet next week, Friday. Okay. Have a good weekend.
Thank you, sir. Bye.
So you're welcome.
Thank you, sir.
You're welcome.
So the engineering technology lecturer has sent some link, Google Meet. So I put it across. Let's join because it's the lecture will start 1:30, but he wanted to start right now.
Should we start right now or 1:30?
Is there?
You want us to start right now or we should wait to the 1:30?
You start 1:45. But he called me
Okay,
and asked me
1:40.
whether we are ready. So let me just inform him that we are ready if you want to continue, you want to start.
So I think
Because the
okay.
French
So by
French
you
lecture French lecture too, I heard that he is not available, so he want to miss out tomorrow around 7.
in the evening, okay.
Mm.
But engineer,
Yes,
I
sir,
beg,
boss.
I beg you, if you dey contact them, make you dey beat them say them get past
Pass.
questions. Why?
It be very important.
It be very important. At least sometimes it go make you know them are pattern of exams.
But I be the mass
Uh,
lecture in the flow we already say the thing
uh,
the
some
assignment will be we. Oh.
uh-huh.
So
So that
the
one,
mass
say,
lecture,
oh, if you dey
the
learn,
ma- yeah, in own there, you fit target one topic, to like 2 or 3 topic, then you master that one. By all means,
you master, yeah.
you go come. Cause you say you go bring from all the topics. So
And
functions.
he put there, even if you carry one topic, class, you go kill us. Mass there, one topic alone. Obenya questions bebree.
Hey, baby.
Okay. So you make it communicate plus the lecture and make it.
Mm.
Where Kingsley be? Kingsley he comot. So Charlie, you people, yaira mo ya yaira den. The way yaira ma lecture be about ogbonidi na no odin.
So we are ready.
Yes, you are joining. So how many people are we expecting?
We are expecting 14.
Okay, so when we get started, there is right. In fact, we can start even now.
Okay, so we are joining.
Okay.